Dale, dale.
Okay, welcome back. Now we are going to have a special seminar by Rodrigues, which is one of the directors of the Lambda laboratory. The Lambda laboratory was inaugurated last year, and it specializes in developing particle detectors with low detection thresholds. The research interests are dark matter, neutrinos, and quantum optics. Darío has done his undergraduate and studied here at the physics department at Buenos Aires University. He then did go for a postdoc in physical chemistry, and after that he made another postdoc at Fermilab, where he worked developing the CCD skipper technology. And after that he returned to Argentina to take care of the Lambda laboratory and of the Lambda collaboration.
Thank you, Susana. Thank you to all the organizers for the invitation. I am really glad to be here. Y hola a todos. Gracias por venir. Okay, so my talk will be a little bit different probably because I will talk about experiments and the data of the experiment and how we use this data to put the constraint we already have regarding dark matter. The title is, as you see, direct detection of dark matter and exclusion limits. But I will start with a landscape about which is today what we know about dark matter and what we don't know. So regarding what we know, the question, I think after 10 days here in the school, nobody has the question if dark matter exists. The most of the physicists say, yes, that is not the question. The question is, what kind of particles make dark matter, yes? And of course, you are all familiar with this relationship, 6-to-1, between the dark matter and the ordinary matter, the one we know, baryonic matter. So, in this context, we are ready to ask, okay, what part of the universe is made of dark matter? Or is dark matter part of a dark sector? So is dark matter only one particle we need to discover, like was 15 years ago the Higgs boson? Or is something else? Is maybe a huge dark sector with some similarities with the one we already know, our standard model, but some kind of black mirror of our standard model? There is interactions, probably is in there interaction that we don't know, and there is some new interaction between this dark sector and our sector. All what we know, and this is the reason why we propose dark matter, that there is a portal, and that is the gravity. Without gravity, there is no reason to propose dark matter. But we hope something else. When I said we, I am talking about the people making experiments to detect dark matter, because we need something else, yeah, to have the expectation that dark matter is able to release some kind of energy in our detectors. So this is the scenario. There is a portal, gravity, and we expect something else in order to be detected. What we know about the mass of dark matter? Okay, you can say nothing because 90 order of magnitude is the same as say, okay, I don't know which is the mass. Okay, we don't know. However, depending on which part of this huge spectra you have different behaviors, different kind of particles, and different strategy to look for that kind of particle. And that is my point, because when you want to make an experiment, when you need to look for something, the first question is, okay, can I see the signal that this kind of particle releases in my detector? It depends on the particle, of course, and it depends also, of course, the technology you have. So, regarding ultralight dark matter, or regarding in general the full spectra, there is something that we can do at the beginning. We can ask which kind of behavior has these particles depending on the mass. Thanks to the astronomical observation, we know that in the local halo, the velocity is around 220 kilometers per second. And we also know the density of the dark matter, which is roughly 0.4 GeV per centimeter square. So if we know the velocity using the de Broglie formula, we can have these very nice rules of thumb. I like rules of thumb. I have a few of them for you today, which means, okay, depending on the mass of the particle, the distance, which is important if you are asking about which is the range of interaction, let's say the de Broglie distance, is just the ratio between 50 eV and the mass of the particle multiplied by 34 micrometers. On the other hand, as I already said, we know which is the density of dark matter in our local halo. And this is, as I said, 0.4 GeV by centimeter square. Let me stop here. What means that number for you? 0.4 GeV, what is that in terms of something that you can feel? Because I don't feel nothing regarding that number. How many, what is the amount of dark matter here, for example? In here, in this volume? Something. A number. On what? I have this number. I have this number. Yes? Suppose I'm uniformly distributed dark matter in this volume, which is 3 centimeters square. How the mass of dark matter here is equivalent to which number of electrons, let's say, something we know. Which number of electrons has the same mass as the dark matter in this volume? I want to see. 4,000. Nice. 10 to the 9. Okay. Someone else? 10 to the 6. Someone else? It's solved for you. Yeah.
I would say like a quarter of a mole.
Okay. Something else? No? Okay. He's the winner. I don't know if you calculated this number previously. No? Probably, yeah. Yes. 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 Nice, nice calculation. Yeah, yeah. For sure. This is the kind of calculation I like. Great. 4,000 of electron is the equivalent mass of dark matter in here. Yes? Okay. So we have the de Broglie distance, and we have the distance in between them, because this is just a very, very simple formula. If we put here the mass of the dark matter, and we make this ratio, now we have the distance, the average distance between them, depending on the distance, on the density, sorry. So we can divide both and get this very, very simple rule of thumb. Why? Because you see that the relationship between the de Broglie distance, which is a measure of the chance of interaction, and the distance between the particles is a function of the mass of that particle. Okay, we don't know which is the mass, but if we try a mass here, we will find a relationship. And what you are seeing here is that if the mass is greater than 50 eV, yes, this ratio will be lower than 1. So it means that the particles are far enough to don't see each other. In that regime, above 50 eV, we are talking about particle-like dark matter. They behave like particles. However, if in here you put a mass lower than 50 eV, 1 eV or less, 10 to the minus 6 eV, it means that they behave like a wave. They are a field coherently interacting, yes, like the axions. So first thing that we can say regarding this 90 order of magnitude is below 50 eV, we have a behavior, and we have a different one above 50 eV. Ultralight dark matter must be a boson. Why? We can also make something regarding particles with this very huge spectrum of mass. If we have, it must be boson, because for these energies, if you have a fermion, because of the Pauli exclusion principle, we cannot explain why we see dwarf galaxies. Yeah? And this is a reason to say, okay, below that, here only bosons. Here, fermion. We can have boson here, but in here, only bosons. And also, it can be used to explain why 10 to the minus 22. Because, again, by using the same equation, if you put this number, 10 to the minus 22, here, and you calculate with this very, very simple rule, which is the size of interaction, this is 10 to the 18 meters, something like this, the size, roughly, of a dwarf galaxy. Yeah? So, we have a little bit more information regarding dark matter. Let me go to the next step. Okay, we know something, but we would like to detect this kind of particles. It's not easy to classify the different way in which the humanity try to find a way to directly detect dark matter. But let me use these three kind of strategies. Yeah? It's not the only one. You can find in the bibliography, for example, indirect detection, which could be this kind of measurement and other classification. But for the sake of simplicity, I will talk about these three kind. First, production of dark matter. Accelerators like the LHC can produce dark matter. Because as you know, in this kind of accelerator, we can collide proton by protons. If dark matter exists, when a proton collides with another, dark matter can appear as a result of that interaction. What is the strategy to look for dark matter? Because suppose that dark matter appears in that kind of collision, then you need to see if dark matter is there or not, and the problem is to detect dark matter. So one strategy, the one that people used to follow is, okay, let's calculate how many energy we have at the beginning and how energy we have at the end. What is the momentum before and what is the momentum at the end? If we have missing energy, it probably means that new particles appear and then I was not able to detect it. And it could be dark matter or a neutrino, of course. It happens all the time, neutrino escape of the detector. But, okay, this is a way, a very powerful way to look for dark matter. The other one is precision measurement, which is essentially, we have a very, very precise standard model which is able to predict the cross-section of interaction with excellent accuracy. Okay, we can improve our uncertainty. We can improve the uncertainty. We can reduce it. We can measure better and better and better. And if dark matter exists, because of a new channel of interaction in that experiment, probably, if the standard model prediction is here and I have this uncertainty, I improve my experiment, and at some point, I see this. I see that my measurement is not compatible with the standard model prediction because I reduce the uncertainty until I see a significant difference between my result, what I observe, and what the standard model predicts. In that case, I can say, okay, there is something else, some new interaction, some new force, some new particle, something that was not included in my calculation that can explain why the prediction doesn't fit with my result. Yes? This is a second strategy. Very, very useful. A lot of experiments based on this idea. The third one, which is the main topic of my talk, is direct detection. We are living on Earth, and the Earth is moving through the dark matter, the halo, at least, of our dark matter. So we can wait until a particle of dark matter interacts with our sensor. If the dark matter interacts with our detectors, we expect to see some kind of signal, small, very tiny signal, but if that signal is above our threshold, we will see events that we cannot explain as background. In that case, we are not creating dark matter like in the accelerators, and we are not improving our uncertainty about the cross-section. We are waiting for the dark matter to interact with our detector. Yes? Something important here. First, production is not accelerator the only way. Nuclear reactors are also a place where dark matter can be produced. In a nuclear reactor, we have a huge amount of neutrinos, a huge amount of gamma rays, and they, by means of some kind of Compton-like interaction, can produce milli-charged particles, which could be part of the dark matter, and they can also produce axions, the ultralight dark matter candidates. So we have 3 different strategies, and let me say a few words about this one, and then I will go in details about this one, which is the one we use in our experiments. So regarding ultralight dark matter, we already discussed this limit. Here, there is a short list, because it's not the full list, of experiments which are dedicated to look for axions, ultralight dark matter. The one behaves like a coherent oscillating wave or a field. In general, just to keep in mind, the strategy of these people is create a cavity with a very, very strong magnetic field. Very strong means above 1 Tesla, probably 8, and expect for the dark matter to interact with the field, an action, and makes a transformation from an action, create a photon, a microwave in general. And then, of course, a photon is one of us. It's a standard model particle. We can detect it with any of the many techniques we already know to detect photons. So these strategies are not all the same, but in general are around the same idea. A very strong magnetic field in order to decay an action in a photon and then detect a photon. Yes? I already talked about accelerators and how accelerators can produce dark matter, but there is not only way to do that. One way is the one from the LHC. They can collide protons, and then phaser, for example, is an experiment which is in the far forward region, roughly, if I remember good, is something like 500 meters away from the point of the collision, looking for elusive dark matter sectors. Yeah? Because don't worry about the baryonic matter in between. It's a shield. It's good. You can be 500 meters away, and this is enough to stop all the other particles and just receive neutrino or dark matter. Mini-boon is an experiment which is aimed to neutrino physics at Fermilab, and also use neutrino produced by a beam dump. In this case, are protons that are stopped, yeah? No collide with another proton. And it creates a lot of radiation, yes? Mini-boon look for neutrino, but in general, the most of the experiment looking for neutrino physics has the same challenge as the people looking for dark matter. So this experiment is also sensitive to some kind of dark matter particles using the same detector, which is the one you are seeing over there on the right. It's a huge camera with hundreds of tons of a scintillator. If the particle interacts with the scintillator, then it emits light, and the light can be detected with these photomultiplier tubes. I will talk about this on the next slide. Another way is not using protons. Instead, we can use electrons. And again, we can collide electrons in a fixed target and search for the missing momentum of the electron after passing through this piece of material. again, if we see a difference in the momentum before and after that we cannot explain with the baryonic interaction, probably it is because that radiation produced dark matter. Yeah? But it's not the case of direct detection, because you are creating dark matter and then looking for missing energy. And this is just a very short list of a very huge number of experiments using this strategy to look for dark matter. Okay, but we are living on Earth. On Earth, not in Earth. It means that we make our experiment on the planet. So if we are looking for direct detection, remember, we are expecting for the dark matter to interact with our sensor, we need to know roughly which is the amount of dark matter around Earth. So now you can tell me which is the amount of dark matter in the volume of the Earth. Like this. The density is the same. And all can make the same. Yeah. 3,000 electrons is the equivalent mass for the Earth planet. What do you think? In kilograms, what do you think? 1, 10 to the 3, 10 to the 6, 10 to the minus 6, 10 to the 2, nice. In grams or kilograms? Nice. Good. Yes, 10 to the 2. 5, 10 to the 2. 8. Okay, but we cannot make our experiment inside the Earth. We are living on Earth, so we are interested in the amount of dark matter around the Earth, yeah, close to our detector. And this is just 2 grams. Yeah, and we are very confident about this number. So 2 grams is true. Someone can say, okay, 2 grams is very, very difficult. No, if you sum up all the coronavirus during the pandemic, it's nothing in comparison with 2 grams. And everyone can see the effect of the pandemic. Yeah? The same for cosmic ray. If you sum the mass of the particles interacting with the atmosphere and producing the aurora boreal, I don't know how to say in English, this kind of light on the sky, you don't need an experiment to see it. You need to be probably in that place in the correct moment, but you can see it, and the mass to produce this effect is nothing in comparison with 2 grams. So the problem is not that we have very, very little amount of dark matter. The problem is that this matter is almost not interacting with our matter. That is a problem. Yeah? Okay, again, we have this very huge spectra for dark matter. And we are interested in knowing in which kind of mass is in the case of only one particle. Of course, I started to talking about a dark sector. Probably there are a lot of different kind of dark matter particles interacting between them, annihilating between them, producing X-rays, 3.5 keV X-rays from the universe probably coming from the annihilation of dark matter. There are a lot of opportunities to make physics here. But if I wanted to detect these particles, I need to know which is the best strategy. And if we have a detector, a baryonic detector, not a dark matter detector, we have atoms with a nucleus and electrons around. So we can look for the signal that a dark matter release in the detector when interact with the nucleus or with the electrons. Yeah, these are 2 big strategies for the people looking for dark matter in the direct detection strategy. So, what is the difference? Here we have a nuclear recoil, here we have an electronic recoil. Again, let me make some very simple calculation to get some rule of thumb and just to learn where is the most convenient case depending on which kind of particle you are looking for. Yeah? First, in an elastic interaction of dark matter with a nucleus, the energy, the recoil energy released by this interaction the recoil energy of the nucleus after the interaction with the dark matter goes like 1 eV, the ratio between the mass of the dark matter and 100 MeV, to the square. And then this ratio is equal to 1 because, for example, in the case you are using silicon, silicon has 14 protons, 14 neutrons. It means a mass of 28 GeV. So that is 1. Well, if we have a particle with the same mass of a proton, which is 1 GeV, this ratio goes like 10. Square means 100 by 1, 100 eV. So 100 eV is something easy or something very hard to be detected? What do you think? 100 eV is hard to be detected. Yeah? It's not impossible. There are many strategies, many technologies today able to detect 100 eV, but it's not so easy. The most of the detectors are able to detect energies about 1 keV. We have detectors able to detect 2 eV, like the one I will talk in a rush. But let's say 100 eV is challenging. It's possible, but it's challenging. Okay. What about this case? In this case, this is the kinetic energy of an electron after the interaction with matter, dark matter in this case. You see here, the factor is 100 eV instead of 1 eV. And again appears the same ratio as here, mass over 100 MeV. The good news here is if you have a particle with 100 MeV, you have the same signal as here. So, in general, it's not for all the experiment, but in general, when you are looking for heavy particles, you are interested in nuclear recoils. Like the one can produce WIMP, I will talk about WIMP in the next slide, but WIMP means weakly interacting massive particles. Massive means between 1 and 10 to the 4 GeV, between 1 and 10 to the 4 protons. In that case, the people go for this strategy, just looking the energy released by nuclear recoil. In the other case, which is our case, when we are looking for light dark matter, we are interested in the recoil of electrons. In this case, we follow this equation. Okay. But the life is not so easy. We have two problems when we follow this strategy. The first problem is the quenching factor. Quenching factor is the relationship between the energy used by the nuclear recoil to ionize electrons, which are the one we can observe, divided the energy that the nuclear recoil has. It means which fraction of the energy the nucleus has used to produce ionizing electron. And this number is below 10%, 5%. And nobody knows if this number is 0 below 50 eV. We don't know. Nobody was able to measure with enough precision that number. The other point, which is very important point, is 7 is coherent elastic neutrino nucleus scattering. It's a standard model interaction that was predicted 40 years ago, but was observed for the first time just 5 years ago. We know that the neutrino can interact with the nucleus like the nucleus as a wall, as only one particle. The result is that the cross-section goes like the number of neutrons to the square. So for silicon, it's a factor 200. Yeah? Okay, what is the problem? We are living inside a very huge sea of neutrinos. So if we have a lot of neutrinos interacting with our detectors, and they, because of 7, can release a signal, when we reach that level of sensitivity, how we can find dark matter if we have a huge signal because of neutrino? Solar neutrino, atmospheric neutrino, reactor neutrino. That is the case of the detection of WIMPs. WIMPs, as I already said, weakly interacting massive particles, was a very, very exciting candidate during the last, let's say, 30, 40 years. A lot of experiments were done in order to find these particles. Why? Not because the mass is between 1 and 10,000 protons. It was important because it would be produced in the early universe shortly after the Big Bang. And when you calculate the abundance, it roughly match with the amount of dark matter we need to explain what we see on the sky. So it was something very nice. Also, there is some implication with supersymmetry, which was another reason to look for this particle. And there are a lot of experiments. This is, again, a short list looking for that particle. Xenon 1 ton is probably the most famous of them. And it means that these people has 1 ton, in this case, of xenon, waiting for the dark matter to interact with xenon, with the nucleus of a xenon. If it happens, the energy released by the nucleus can excite the xenon, and then when the xenon releases the energy, it produces light. And this light is again detected by some photomultiplier tubes. This huge amount of xenon is probably the place in the world with the lower background ever. Because if you are living inside, you have 100 events per ton per year of environmental radiation. Here, in this place, I have 100 events per people per second instead of per year. 1 year is 10 to the 7, p 10 to the 7 seconds. Okay, you see the difference. 10 to the 7 times less radiation inside. This is the level of background you need to be under control to make this kind of experiment. And of course, these people is working in the National Laboratory Gran Sasso in Italy. Yeah? It's roughly the equivalent to 1,400 meters underground. It's inside a mountain. It's not underground, but they have more than 1,000 of rock above the detector, shielding the detector from the cosmic wreck. Okay, but what is the problem? They improve a lot the limit, a lot, during the last 40 years, and they are close to reach the neutrino floor, the background produced by neutrino coming from the sun, from reactor, from the atmosphere. After this point, probably, they say, okay, I can look into the neutrino floor. There is some people saying, it's not a floor, it's a fog, neblina, for the people speaking in it, yeah? So it is not so hard, we can still ask money to make one more measurement. But the community is, during the last 10 years, thinking about another possibilities. And this is the one I will talk right now. Direct detection of light dark matter, yeah? No above the mass proton, below the mass proton, yeah? But above 50 eV, like particle behavior. We have silicon, a piece of silicon, and if the dark matter interacts with an electron and release energy enough, when I said energy enough, in this case, it's just 1 eV is enough to move one electron from one band to the other one, and we can see that electron trapped in one of the pixels. A CCD camera is something very, very similar to the one you have in your phone. Yeah? It's a piece of silicon with many, many pixels. There are a lot of experiments running underground in order to see dark matter using this technology. The first one was probably DAMIC. Sensei with a different kind of technology, which is called Skipper CCD. DAMIC M and Oscura are the next generation of this experiment. So, charge coupled device, as I said, are very, very similar to the one you have. You have CMOS. It's not a CCD, but it's similar. And this is a picture of the picture that the guy who invented the picture take using this technology. Not exactly this, because this is the detector we use today to look for dark matter, but is the result of 40 years of investigation around this topic. How we measure? Now I will go in detail about this strategy, the one we use, just to put in with details how, when we know the theory and we make an experiment, we can establish a new exclusion limited for dark matter. ¿Ya? ¿Cómo estoy de tiempo? Okay. So, this is a piece of silicon waiting for the dark matter to interact. But of course, before dark matter, another kind of particles are interested in interact with our sensor. When it happens, we see how the electrons move excited by that kind of radiation are trapped in each of these pixels. Each of them has 15 by 15 micrometers, yeah? And the thickness of the detector is 700 micrometers. The full sensor has a mass of 1 gram instead of 1 ton of xenon. Yeah, this is the difference with the other experiment. Okay, we have this. Now we need to read out. We need to know which is the amount of electron in each of these pixels. How do that? We first move the charge all to the one step, one row down. See? From here to here, one row down. And then we move these on the right. You see these numbers? To the right. Yes? And again, to the right. When we put the first charge here, which we call summing well, until here, I am talking about a charge coupled device, a conventional one, a CCD. The new technology, the skipper CCD, can make the following. We can move the charge between the summing well and the sense node as many times as we decide without destroying it. So we put the charge in the sense node, we measure the charge, and then we move the charge back. Again, we move the charge to the sense node, and then we move the charge back. And then we move the next one. We go to the other package of charge, 1571 electrons. Okay, the same. I move on the right. I sense the charge. I move the charge back. And I move the charge back. What is the result if you measure 100 times the charge? At the end, you will use the average value of these 100 measurements. The average has an uncertainty. Let's go 1 over the square root of the uncertainty of only 1, which means that if you measure 100 times the charge, the uncertainty is a factor 10 less than if you measure only 1. If you do that 10,000 times, you have not noise. What is the result of having not noise? Okay, the result is this. You start with a picture like this. When you see nothing because of the noise, this is the best CCD ever without skipper technology. Yeah? You take a picture of the noise, and you see this histogram of charge here. But when you want to see what is the real charge in each pixel, you can use this technology to measure the charge in each pixel as many times as you decide without destroying it, reducing the redundant noise as low as you decide. After doing that, the result is that instead of seeing nothing, you discover that you have only 1 electron here and nothing around. So with this technology, we are able to count electron by electron, but not only 1, 2, 1,000, 1,001. We can distinguish 1 electron in a very wide dynamic range. Okay, this is very sensitive, so it's a good candidate to look for dark matter. What we can do, we can take one of these and go underground. First, 100 meters underground at Fermilab in the US, and put just only one of these. Only one means 1 gram of silicon. And again, wait for the dark matter to interact with our silicon. Okay, what do you see? Something like this. When you take a picture with this very sensitive technology, you see muons all the time. Here, as Susanna said, we have detectors. We have this kind of detector just in the 2nd floor in this building. And when you turn on the detector, after a few seconds, you see muons, because we have a lot of muons around. Yeah, you know, 1 muon per minute per hand. Okay, but we also see X-rays, electrons, a lot of kind of particles that we are pretty sure that they are not dark matter. So we need to develop strategies in order to see what we want to see. Is sun event compatible with dark matter? So what is the way? Just get rid of all what you know that is not dark matter. This is the first step. Yeah.
How can you distinguish between the different particles? How do you know if it's
Yeah. In general, the reason why I said this is a muon is because a muon coming from the cosmic ray had an energy above 2 GeV, 4 like. And the mass of the muon is 200 times the mass of an electron. So the probability for a muon to interact with a nucleus is very, very small. So they can pass through the matter without change the trajectory. So when you see a right line, it is a muon. However, if you are an electron, because the mass of an electron is similar to the mass, is the same of the mass of the electron in the lattice of the silicon, you have a lot of scattering, and this move like this. And if you have an X-ray, the X-ray interacts, let's say, 1 keV or 10 keV. The first interaction is a photoelectric one. It releases all the energy to one electron in the lattice, and then the electron makes something similar to that, but with very, very small energy. And this is the reason why we see just circle. Yeah? But there are other ways. We go underground, and the number of muons decrease drastically. We put an X-ray source, and the number of dots increase drastically, and we see electrons like this. Yeah. What we expect for dark matter is only 1, only 2, only 3 electrons. This is the answer to your question. This is what we expect for dark matter. We have, thanks to the work of the people making theory, we have a cross-section. We have I will show you soon. We want to calculate using the dark matter in the halo, the density, the velocity, and which kind of candidate we are looking for, and which kind of material we are using to detect it. We can calculate which is the expected rate. Of course, you need to set a mass and a cross-section, yeah? Which is the both parameters we are interested in. Suppose that we set it, we get this spectra. So there is a scale factor here, which depends on the cross-section. But doesn't matter about that. What is important here is the relationship between the probability of having 1 electron produced by dark matter and the probability of having 2, 3, 4, and so on. What you are seeing here, this is a logarithm scale, which means that the probability of having 3 electrons is 1 order of magnitude less than the probability of having 2. And something similar when you go to 4. It means 5, impossible. No one you will see 5 events because of dark matter, because if you see this, the probability of having 4 is 1 order of magnitude above that. So what we want to do with this kind of images, clean it as much as possible in order to see only the part of the pictures able to have only 1, 2, 3, 4 electrons. No more than that, because for this technology, the probability of having an interaction due to dark matter is very, very unlikely here. Mariano Cavalier is the guy who was working a lot on this during his PhD. He finalized the PhD just a few months ago and make a lot of effort in reducing the number of events that we observe that we don't know what it is. O sea, is dark matter or is something else? If we reduce everything, we are more sensitive to dark matter. So how we do that? I will go a little bit fast here. We have the image. First, we said, OK, hot pixel and hot columns are defect of our detector. Get rid of here. I know that my detector is not working well in that point. Out. I know that for the way I move the charge, I already explained how we move the charge. There is a probability, very, very small, but not 0, of the charge to appear on the right side of the, for example, a muon track. Because we have a huge amount of charge here, and when you move it, if you have a probability 10 to the minus 6 of losing 1 electron, okay, after 10 to the 6 movement, you will have one electron left. So all of them must be removed. So what we do is say, okay, we have a muon. I will not see around the muon because I know that around the muon there is an opportunity for a charge to appear, charge that is not dark matter. In addition, 2 years ago, we see that around muons we have more the rate of one electron event is higher than far away from the muons. And it is because the path of the muon for a piece of silicon produces Cherenkov radiation. Cherenkov radiation can travel through the pixels, and when interact with some pixel, let's say 5 pixels away, that interaction through photoelectric can produce an electron. So we see more electron around the muon. So each time we see a muon, we say, okay, this part of the image must get rid of because it's contaminated because of the Cherenkov radiation produced by the muon when it passed through the material. And high energy halo is exactly that. High energy halo is all the image I am not interested anymore because it's contaminated because Cherenkov, and also Bremsstrahlung, which is the radiation emitted by a particle, a charged particle, which is not traveling a constant velocity. So, what in this this is a piece of picture. It's not the full picture. It's just a piece of picture to explain how we work. But you see, survive at 5%. Okay, in this 5%, we will look for dark matter. Yeah, we do that over a huge amount of pictures, and the result after doing that is we have more than 1,000 events of 1 electrons, 5 events of 2 electrons, 0 event of 3 electrons, and 0 event of 4 electrons. We have never seen a pixel with 4 electrons in any of our images. We have never seen a pixel with 3 electrons. And we have seen only 5 pixels with 2 electrons. And a lot of them with 1. But, of course, that is what we expect. Do you remember? The rate for 1 electron is 1 order of magnitude higher than the rate for 2, and so on. So this is consistent. Okay, but we can claim that these 5 electrons are dark matter? Of course not. We can do that. The last part of my talk is how we use that result to put an exclusion limit. How we use this result, combine it with the theory to say something about the cross-section of the dark matter. And the recipe is like this. You have what the theory said. If you have some kind of cross-section, this is the number of events you expect. Again, these spectra change if you change the density of the halo, the velocity of the halo, that we know, we put this number because the people making this measurement has really nice numbers about that. But we need to put some mass. We don't know which is the mass. And we put something in between 10 to 1 GeV. And then we need to put some cross-section, because without the cross-section, the model is not able to say how many events you expect in your detector. OK, we set the cross-section, and we have that. Then we need to move the cross-section to fit our result. But before that, we need to make statistics. Why? Because we have what the model said that we need to expect. And we have our result. How we can combine result and the theory to get this kind of plot. Let me say a few words regarding this plot, because it's very, very important to understand now what we are looking for when we setting exclusion limit, because otherwise it's impossible to understand the strategy. This axis is the mass of the dark matter. It's between 1 MeV and 1 GeV. Here is a proton, yes? And here is 1 eV. This is a range in which we are moving. For each mass, we have a cross-section. It means a probability to interact. So what this kind of plot is telling us? It tells that if the dark matter has a mass of 10 to the 2 MeV and a cross-section of 10 to the 34 centimeters squared, with a 90% of confidence level, I will say that pairs of parameter doesn't exist. Why? Because if the dark matter with 100 MeV has this cross-section, in my experiment, I expect to have more event than the one I observe. So, because I observe 0 event, I know that this region is not possible. The exclusion region is the one with the pair of mass and cross-section incompatible what we observe. Yeah? In the other way around, if the dark matter has this number of cross-section and mass, it's impossible to see nothing, because with this cross-section and this mass, in my detector should be a lot of electrons, and I see 0. And this is the way, like all the experiment, use the theory to put this limit. Of course, it's not impossible for the dark matter to have this energy and this cross-section, because these limits are setting using a 90% confidence level. So there is a 10% of probability of observing 0 because of a statistical fluctuation. Yeah? Okay, how we do that? What we do is, we observe 5 electrons. For the sake of simplicity, I will talk about 2, 3, and 4. The channel with only 1 is not included here, but is in the paper. You can go to the reference if you are interested in the details. 5 electrons, 0, 0. Okay. I also know which is the effective exposure. It means I know how many grams of silicon I have. I know how many days the silicon was exposed to the dark matter. And then I know what was the effect of all that quality cuts I apply in order to reduce muons and all the background. Yeah? Yes? Sheet day. Ah, sorry, G, this one. G day is gram days. Gram, the G is because of gram. It's mass by time is the unit we use to measure exposure. Because it's the same if you have 1 gram during 1 week or 7 gram only 1 week. The exposure is the product between the time and the mass. Yeah? Ah, nice question. Freezing is one of the models to explain how the dark matter appears. It's freeze in and freeze out. These lines is where we expect to find the cross-section of the dark matter if the freezing model is correct. So this line is very, very interesting because it's saying if you reach this point, you will be able to test a very, very well-motivated theory to explain why we have dark matter. Yeah? Yes. So thank you for the question because it's nice to mention. So I will go fast because I have 10 minutes. Okay. So we observe 5 events. And we are particle physicists. It means we are frequentists. No Bayesian. It's good Bayesian, nice, but when you have 5 events, you cannot go for the Gaussian distribution. It's not Gaussian anymore. It's like this. You see a Gaussian, you have a tail over here. So if you have 5 events, only 5, and you want to say, which is the upper limit? First, of course, the number of events in our detector is a Poisson random variable because we have a huge dark matter particles around with a very, very small probability of interact. So it's the best Poissonian example for any case. So if I have 5, I need to find which is the mean value of the Poissonian distribution in order to have the 90% confidence level. It means I pull the mean until, observe, on the left, 10%. I move to 6, 7, I reduce. This number is the integral for 0, 1, 2, 3, 4, and 5, because 5 is what I observe. So the probability of observe what I observe or less is 30% here. If I increase this number, if the Poissonian, which is producing the number of events I observe, has a mean equal to 8, the probability of observe what I observe or less is 20%. If I go 9, I go 9.27, and now I have in the condition like a Poissonian distribution with this parameter has a probability of giving me a number of events like the one I observed, 5 or less, 10%, which means that the confidence level is 90%. This is the frequentist way of setting an upper limit, 90% confidence limit. So instead of 5, I will use 9.25, 27. And now I can divide this number by this number, by the effective exposure, and get a rate. A rate is the number of events I expect per gram per day. Yes? I can do it the same with this, with 0, and say, okay, if I observe 0, which is the upper limit, the same frequentist recipe, I need to go until mu, the expected value for the Poissonian distribution, equal to 2.3, in order to get on the left, it means 0, 10%. On the right, 90%. Okay, 2.3 is the frequentist upper limit with the 90% confidence level when I observe 0. So instead of 0, I will use 2.3. And then I will divide this number by the exposure to get the ratio, the rate. Now, the last step is I have the rate I observe with the 90% confidence level. I will look for the cross-section.
Why are you considering only the 2 electron, 3 electron, and 4 electron events, and not the 1 electron where you have more events?
Yes, we use the one. It was here. Sorry. Oh, but I already showed it one. I excluded here just because in that limit is Gaussian. Because if you have 1,300 electrons, you can use that. We can do that. But here we have 5, and in the other channel we have 1,300. We are competitive with 1 electron. But this, what we need to do, and this is the most interesting part and the most problematic part, is we set the limit saying all what we see is dark matter. Doing that is the most conservative approach. I don't know if you are agree with me, but saying all what we see is dark matter gives me the worst limit. It's the most conservative approach. Why? Because, so the question is, 2 is better than 1, but we also make the calculation with 1, and we publish it. I omit it here just for the sake of simplicity. But yes, I use it. So what we do, we say, okay, I have in this expression, the order 0 is the first line. The second one is order 1, yeah? Here is the information about the detector, about the halo, about the interaction, but all of this is a factor order 1, and this is order 0. Put attention here. If you make here we have the density of dark matter. Density of dark matter. Here, the mass of the dark matter candidate. Yes? Here, the cross-section of that dark matter. So what happened if we increase this number? Of course, if we increase the cross-section of interaction between dark matter and my sensor, I increase this number of expected events. Yes? So what we do is we have what we observe, and we have what the theory said we expect. We increase cross-section until match what we see with the theory. So the cross-section we need to put here in order to recover the rate we observe is the one we will use then to put here. But of course, all of this is for only one mass, because I choose a mass, for example, 10 MeV. With 10 MeV, I go to the calculation, I put the dark matter density, 0.4 GeV by centimeter squared, I put the velocity of dark matter, I put all the condiment, all what we know, and the theory said, okay, with all this information, if you have a cross-section, I will give you a rate. Okay, thanks. I have my rate because I already made the experiment. So we move the cross-section until reach the frequency 90% upper limit of our observation. When we do that, we are here. And please pay attention here. It's very, very important to understand why saying that all what I observe is dark matter is the most conservative. Because if I have a huge of event, 1,000, and say all what I have is dark matter, it turns on a very high cross-section because I need a high cross-section to explain a lot of events. So the most conservative approach when I measure is said all is dark matter. In that case, I need to ask for the cross-section to explain my event instead of background. And it said the worst scenario. Doing that in this range, which is the one corresponding to light dark matter, Sensei, which is the experiment doing using skipper CCD, has the best exclusion limit on the world. The best exclusion limit is this line, and is achieved by using skipper CCD. It was in 2020, but I will finish with the result of 2023, and we are still the best. This is the second part of the experiment, because all the result until here was 100 meters underground at Fermilab. But the experiment now is running 2,000 meters underground in Canada. 2,000 meters underground means essentially no muons coming from outside. In that condition, this is the experiment. Now, instead of only 1 gram, we have 65 grams. With 65 grams, 26 detector, 200 meters underground, this is the result. Now, again, in this range of mass, Sensei has the best exclusion limit for dark matter, and is very, very close to the freezing line that you pointed out. So very, very close to an exciting moment where we can test if this very, very well-motivated theory to explain dark matter is correct or is incompatible with our data. So, last 3-4 slides. There is a next generation. Sensei was the first step with the skipper. There is DAMIC-M, an experiment with 1 kilogram of a skipper, and the next generation is Oscura with 10 kilograms. Remember, one detector is roughly 1-2 grams. 10 kilograms means 1,000 of detectors. Yeah, it's the most bigger camera ever, 24 gigapixel, I think. You must calculate it, but it's the biggest for sure. And to operate this detector, we need to run until 140 Kelvin in vacuum. So for the electronic point of view and engineering point of view, it's a challenge to make this kind of experiment underground. Also, to create this detector, if you fabricate this silicon detector on the surface, you cannot use it, because the muons passing through the silicon during the fabrication produce traps that then are places where the electrons can move faster, can go from the valence to the conductive bands and appear then and produce a background that destroy your experiment. So this 24,000 detector must be fabricated underground in order to avoid for the muons to create traps that destroy the capability of seeing 1 electrons. So I already said, Susan already said, we have a lab here, 1 year old is the lab, in the second floor with this technology, and we are working in collaboration with Sensei, with other experiments, because skipper CCD is not useful for dark matter only. We use a skipper CCD for neutrino physics, for quantum optics, for imagine all the application you can have if you are able to count electron by electron. Yeah? If you have a new one, please tell us. So, last 2 slides. One candidate to dark matter are millicharge. We are also working on the sensitivity to look for millicharge particles producing an accelerator detecting with the skipper CCD. Santiago Perez is a PhD working on this now at Fermilab. And we also put here in Argentina an skipper CCD just 8 meters away from the wall of the nuclear reactor Atucha 2. Yes? And again here, Eliana, she's over there, is making a PhD with this technology to learn about neutrino physics using a skipper CCD. And as I already said in the first slide, I don't know if you remember, but nuclear reactors are also a power source of dark matter, because a huge amount of gamma can produce dark matter by some Compton-like interaction. So we have an experiment running here in Argentina with this technology inside the nuclear reactor looking for dark matter and neutrino physics. At the end, just for fun, during the last year, we were making images with only 1 photon per pixel, only 1. And you have here to start. After doing a skipper process, this is a GIF, but this is a PDF, doesn't work, but you will see the result. After doing many, many measurements, we can reduce the noise in each pixel and be able to detect single photons. And if you see single photons, you see that the first star was there. Yeah? So we already see the first little star, now we go for dark matter. That's it. Neutrino physics? Yes. Neutrino has a lot in common with dark matter. Probably in the other way around. Dark matter has a lot in common with neutrino. Because neutrino is a very elusive particle, which means it interacts weakly with the matter. But neutrino have seen 100 years ago for the first time. However, there is not so many information about neutrino in the low energy range. And neutrino, as probably you all know, is a portal for new physics, because we know that the standard model is, for example, we don't know if the neutrino is neutrino and antineutrino are the same particle or not, Majorana and Dirac description. So what we do is look for, this is the wall of the reactor, yeah? So the other side, 8 meters away, is the reactor. So the reactor has a lot of fissile material producing disintegrations that produce beta decay, and after a beta decay you have neutrino. The amount of neutrino there is huge, 10 to the 17 per second per centimeter square, something like this. When you need to detect something that is very, very unlikely, you have 2 ways of doing that. You can build up a huge detector, like xenon 1 ton, and you can go a place where you have a huge of that particles. That is our strategy. We have only 1 of the detector, no 1 ton. But if you go to the reactor, we have a huge amount of neutrino. What we are expecting? First, we expect that if the neutrino interact with the silicon, produce this kind of coherent elastic neutrino nucleus interaction, which is the reason why we have a floor when I'm looking for dark matter. We first expect to see that interaction. After doing that, we are looking for physics beyond the standard model. For example, gamma can produce millicharge. Millicharge is a very nice candidate because there is no reason to have only particles with 1, 2, 3 electrons of charge. We have quarks, but you know, we cannot have a quark alone. When you try to have a quark, you have another one. Okay, millicharge are particles with 10 to the minus 6 electrons. That is the charge, or less. If those particles are produced in a reactor, we should see some signal in our sensor. So the experiment running at teacher 2 is trying to set a limit to the existence of that kind of particle. And there are a lot of opportunities to look essentially for example, a new interaction of neutrino. Because we know about the W boson and Z boson, but probably there is a 4 mediator, a boson, interacting there. And if that happens, then we can apply the strategy of measuring better and better and better in order to see if the cross-section predicted by the standard model is consistent with what we observe. In the case of we see a difference, we have the opportunity to say, people working on theory, there is a candidate to explain this difference? Oh, yes, for sure. They will have 100 papers to explain the difference. One of them probably with the correct answer. Here, electronic flavor. And yes, because all of them comes from the beta decay. So they are electronic neutrino, and the distance between the reactor and the detector is not enough to the oscillation that you have from the sun to here in order to have a different kind of neutrino. Yes, only electron neutrino. Yeah. Yeah. There is an experiment doing that in China, I think. Yes, because they have two reactors very close. Here we have a 2 and 1 and 2, and they move the detector, and they can see the rate depending on the distance to the detector. If there is an oscillation, the ratio between muons coming from electron and muons must change, and moving the detector, the distance between the reactor and the detector, you can study that case. And yes, there is a 4 neutrino, there is an sterile neutrino, there are many proposals, and you can sense that kind of proposal seeing what you say. Yes, that experiment exists, and it's already running, I think, because I read the proposal a few years ago. I think now there is an experiment doing what you said. Not our experiment, but yes. Okay? Yeah.
How much time do you think these experiments with this technology, skipper CCD, will need to discard the entire space of parameters?
Okay, I think that Oscura probably will be the last. Oscura will be the last experiment with the skipper CCD, because with 10 kilograms of CCD, if you increase a factor 10, 100 kilograms, the effort to this kind of scale in engineering electronics is very, very huge. But what you gain in the limit is just the square root of that number, because it's not linear with the mass. So I think that Oscura will be able, for sure, to pass through the freezing, for sure. And after that, we will reach our neutrino floor, because neutrino floor is not only for the people looking for winds, it's all around. So in that case, we learn to look for dark matter in between the neutrino, or we accept that the dark matter is not able to be detected in that condition. So today, we need to accept that if the gravity is the only way, the only portal between dark sector and our sector, we are not able to detect it. Okay, probably the other way to say, okay, this is our limit, is neutrino floor. But yes, I think Oscura will reach that limit. After that, we need a very, very different approach to thinking these searches.
Okay, thank you, Ivan. Any other question?
Yeah. Sí. Yeah, because if you go at the beginning, that rules of thumb, and you put that mass, you will see that the energy release is nothing in comparison what we can see. Yeah, it's a good question. We have a way to look for ultralight dark matter using skipper CCD, but we are not able to direct detect action interacting with silicon. What we expect is, in the nuclear reactor, a lot of dark matter can be produced because of the gamma interacting with the nucleus, interacting with the uranium inside, can produce actions. That action goes through the matter without any problem. Suppose you have a huge amount of action, and you are a very likely guy, that interact again with your silicon and produce a photon. The same interaction in the other way around. First, action to photon, photon to action, move out, and now action to photon inside your detector. And we can see photons, of course. So we can set a limit for action, creating in a nuclear reactor, because of course this process is create and then create again, go like the square of the probability. So impossible. But the nuclear reactor had a huge amount of gamma. It compensates the very, very, very small probability of having that kind of interaction, and then you can set competitive limit for the QCD actions. The one can explain the strong CP problem, for example, using an skipper CCD inside the nuclear reactor. Yes, there is an opportunity to do that, but this is the detector doing that. But all of this must happen, yeah? It's not direct detection. But in between there is something very difficult to see.
What's the last question?
Yeah, I have two questions. Is this freezing region line model independent?
No, no. Depends. In general, there are two big explanations. Freeze in, and the other one is freeze out. So depending on which of these explanations you have, in one of them, you have a lot of dark matter and then decay to the one we have today. And the other one, which is this one, you have a small dark matter and it is greased to establish in the dark matter we have today. So freezing, and of course, is small dependent because depends in one scenario or in the other one. If the dark matter created at the beginning or if the dark matter was creating until reach the level of dark matter we observe today. Okay?